In this video, we're going to look at optical isomerism and how we can draw different enantiomers, and what a racemate is and how it can affect plane polarized light. An optical isomer is an isomer where it has the same structural formula but a different arrangement of those atoms in space. In particular, optical isomers have a chiral carbon. And a chiral carbon is a carbon which is attached to 4 different groups. So for example, we could see the carbon drawn in the centre of this tetrahedral shape would be a chiral carbon because it has 4 different groups attached to it. It has a hydrogen group, a CH3 group, an OH group, and an NH2 group. So because it has 4 different groups attached to it, we could say this carbon here is chiral, therefore this molecule would have optical isomers. We'll look at exactly what the 2 isomers are in a moment. The carbon at the centre of this tetrahedral would also be a chiral carbon. This is because it is also attached to 4 different groups. It's got the hydrogen, the NH2, the CH3, and the CH2-CH3 group. Now, even though this carbon here is attached to other carbons, the definition of a chiral carbon is one which is attached to 4 different groups, not 4 different atoms. So you have to take into account everything attached to that carbon. So, a CH3 is different to a CH2-CH3, therefore these 2 groups are different even though they both start with a carbon. So this carbon is still chiral because there are 4 different groups attached. For each chiral carbon in a molecule, you'll have what are called 2 enantiomers. So these are what we call the different isomers. Each enantiomer is a non-superimposable mirror image of the other. A bit like how your hands are. Your hands are mirror images of each other, but you can't place them identically on top of each other, the mirror images, just like the molecules shown in this image are. You need to be able to draw 3D representations of enantiomers, so we're going to look at an example of how to do that now. There are different stages in the process of doing this, so we're going to look at how to draw the different 3D representations of 2-bromobutane. The first step is to locate the chiral carbon in the molecule. It's easy to do this by drawing out the molecule simply first, and then we'll turn it into a 3D representation. By writing out the structural formula of the molecule, you might be able to spot the chiral carbon, but you could get asked to do this for some complicated molecules in your exam, so it's best to draw it out as a displayed formula to identify that chiral carbon. In this case, it's quite obvious which carbon has got 4 different groups attached to it. The one highlighted in yellow is the only carbon which has got 4 different groups, therefore it must be the chiral carbon. Once you've identified the chiral carbon, we need to redraw that molecule in a tetrahedral shape with the chiral carbon at the centre of it. It can help to draw another simplified version of this diagram, shortening any of the groups attached to the chiral carbon. So using this simplified diagram on the right, we can now draw it again in a tetrahedral shape with the chiral carbon at the centre. So we've now drawn it as a tetrahedral with the chiral carbon in the centre. We've included the biggest group here at the top. This will make it easier in the next stage. Be careful when you're drawing groups, for example the CH3, making sure that the carbon is still directly bonded to the other carbon. We need to make sure we draw groups like these accurately, otherwise you could lose the marks. The next step is to draw a mirror line and draw our tetrahedral structure in its mirror image. The easiest way to do this is to draw the mirrored tetrahedral structure first, and then add in all the additional groups. And now we have drawn both enantiomers for 2-bromobutane. Optical isomers can also interact with plane polarised light. Plane polarised light is light where the waves vibrate in a single direction, so you can think of it travelling in a single direction. When plane polarised light passes through an optically active mixture, the molecules interact with the light and rotate the plane of vibration of the light. The two enantiomers of an optically active mixture will rotate the plane polarised light in equal and opposite directions. This means that since a racemate is made up of an equal quantity of each enantiomer, and each enantiomer will rotate the plane polarised light in a different and opposite direction, a racemate will not be optically active because it will not rotate plane polarised light, because within that racemate, each enantiomer will cancel each other's light rotating effect out. One will rotate the light clockwise and the other anti-clockwise by an equal amount, therefore the mixture will not be optically active. If you had a mixture of a single enantiomer, that would rotate the plane polarised light, which in a laboratory setting you'd be able to measure